As you can see from the title of this video, this leads us into Chapter 8, which has all to do with chemical reactions. In this first video, a lot of definitional things, so I found it easier to put them up here on the overhead and talk through them as much as possible, as opposed to just rewriting them up there on the board. If you're in class, you have all these things down, but if not, you want to copy these down, so pause as you need to get yourself your definition. We're coming off a chapter where we learned how to take names and formulas and make them interchangeable. We learned how to name compounds and predict formulas. Now we are ready to really evolve into the whole idea of chemistry. Right? We started with atoms and learned what they are and properties they have. Then we pushed into what happens when two atoms come together, form a compound. Right? We learned how to find the formula of that compound. We learned how to do things like find the percent composition of it. We learned how to name those compounds, and we learned how to empirically determine in the lab their formulas. Now we're ready to decide what happens when atoms and molecules or molecules start to interact with each other and change form. And that is what chemistry is all about. It's about two things coming together and converting them into something new. And that is what a chemical reaction is. It's a process by which one or more substances are changed into one or more different substances. So I take an atom of oxygen and an atom of sulfur and they slam together, and they're now no longer O and S separately, they merge to make something new that has entirely new properties. There is a shorthand for representing that process. We call it an equation. A chemical equation represents, with symbols and formulas, the identities and relative amounts of reactants and products in a chemical reaction. It tells us what things are interacting with each other and what things are forming. I threw out the idea of reactants and products here, so let's talk about what they are. Reactants in an equation are the substances that undergo the change. They are the things that are about to change identity. They always go on the left side of an equation. Products, on the other hand, are substances that result from the chemical change. They're the after the molecules collide and break apart or reform or rearrange. That's what we call the products. They are always on the right side of the equation. So if I look at a generic equation, like this one up here, we have Na2SO4 plus CaNO3 making CaSO4 plus 2NaNO3. Coming off a chapter where we learned how to name things, hopefully you could say that Na2SO4 is sodium sulfate, CaNO3 is calcium nitrate, CaSO4 is calcium sulfate, and NaNO3 is sodium nitrate. If we're defining things as reactants and products, the reactants fall to the left of this arrow, which divides the equation into two parts. The reactants are over here. These are the molecules that are going to collide and get broken apart to reform something else. The Na2SO4 and the CaNO3 are what we call our reactants. Our products, on the other hand, fall to the right side of the equation. Right? CaSO4 and NaNO3 are what is going to be formed when these things collide with each other in the correct fashion. So knowing that it happens is one thing, but when we get into the lab, physically, how can we know that a chemical reaction has occurred? Do I wait forever and then just test? Right? There are signs, physical signs that tell us a chemical reaction has occurred. Here are some of those signs, and if you'll notice, we learned about these in Chapter 2. If I mix two things together and I evolve heat or light, that means that a chemical reaction has occurred. Right? If I evolve heat, something gets warm, that means it's what we call exothermic. If I evolve light, like burning something, right, that's a sign that things are changing identity. Things getting cool would function the same way. Production of a gas. Sometimes the stuff we make as products form gases. How do we know there's a gas? Most often we'll see bubbles. If we're mixing liquids together, that indicates a gas has been evolved, and that's a sign of a chemical reaction. A change in color a lot of times will indicate that we have had a chemical reaction. And that gets linked with this one here, formation of a precipitate. And remember, a precipitate is just when we take two liquid substances, put them together, and they form a solid. Well, sometimes that solid emits light at a different wavelength than the liquids, so it has color to it. And that is why you'll see a color change. Now, I can change the color of something without causing a reaction. I can put drops of food dye in it, and they aren't reacting. So changing a color, you have to understand, is a byproduct of forming a precipitate most often. So these are the signs that a reaction has occurred. Well, if you notice, there's other characteristics about equations that you'll see up here. There's little symbols after each of these compounds. There's this arrow. So I wanted to discuss what those are so that we have a common plane, so to speak, with the idea of terminology. So I have a different overhead there for you. And in your notes, call this symbols within equations, if you're taking class. And some various symbols that we'll see within equations and what they mean are as follows. Sometimes you'll see that arrow that divides the equation into two parts. That arrow has a name. They call it the yield sign. And all the yield sign does is it divides an equation into the reactants on one side and the products on the other. Other things you'll see are parentheses with little letters. Parentheses with letters in them are telling you the phase of that particular compound or element. If something gets a G next to it, that means it's a gas. If something gets an L next to it, no surprise, that means it's a liquid. If something gets an S next to it, that means it's a solid. Those are pretty straightforward. A little bit of a new one would be if something has an AQ next to it. An AQ stands for aqueous. And all aqueous means, and you may want to jot this down, is dissolved in water. Okay, a substance dissolves in water. Imagine you have salt. If I take salt, which is NaCl, like the stuff we eat, and I put it in water, the salt goes away so that you can't see it. But the salt is still there. You could taste it inside the water. So we didn't get rid of the salt, we just changed its form. That is what an aqueous solution is. It's still NaCl, it's just been dissolved in water, and that's why aqua, meaning water. Three other things you'll see have to do with the yield sign. The first one is if you see a yield sign with a triangle above it, and we've done some experiments where we have seen that happen. A yield sign with a triangle above it means that heat is needed for a reaction to occur. Two other less familiar ones would be a broken line above an arrow, and I always say it looks like a lightning bolt, and that helps me think of something. Hopefully, if you're like me, lightning bolt makes you think of electricity, and that's exactly what that broken line above an arrow means, is electricity. And then lastly, sometimes you'll see a yield sign with a formula above it. That's not a reactant or product, it's a chemical that goes into the mixture that causes the reaction to go faster. And that is given a name. They call it a catalyst. A catalyst is something that speeds up a chemical reaction without actually participating in it. The catalyst kind of acts like a boat. It provides a surface for the molecules to come together and react, so that is why they go faster. So these are various symbols that you will see in the equations that we go through in this chapter. Right, some other things that we'll do in this chapter also have to do with counting atoms, right? Figuring out how many of each element there are. So to take a look at that, I'm going to shift up to the front board, so you have to give me a second to readjust the camera, and then we'll pick up right there. So like I was saying, the other part of understanding equations is being able to count atoms that are in equations. Right? So call this just that in your notes. And the reason that you're going to have to learn how to count atoms is that an important part of a chemical equation is that we have the same number of atoms of an element on both sides of an equation. Earlier in the year we learned a name for this. It was called the law of conservation of matter. It says matter cannot be created or destroyed in a chemical reaction, which means that things can rearrange, but they can't go away or they can't appear out of anywhere. So if we're going to learn how to count atoms or refresh ourselves, let's take a look at some examples. Let's say I compare KNO3, which is potassium nitrate, with 2 in front of the atom KNO3. Because what you're going to learn is we can put coefficients in front of things when we're working with equations. If I wanted to count how many of each atom there are, the first thing I do is list how many of each element. So I see that I have K, N, and O. The subscript tells me how many of each there are in one of that particular molecule. So in this, there's a 1 here, so there's 1 potassium atom. In the N, there's a 1, which means there's 1 nitrogen atom. And lastly, there's a 3 after O, which means there's 3 oxygen atoms. If we were going to do the same thing with this coefficient in front, we would say, I still have K, N, and O. And the only difference is this coefficient distributes into those subscripts like it would in math class. So I have 2 times the 1 for potassium, so I have 2. I have 2 times the 1 for nitrogen, so I have 2. And I have 2 times the 3 of oxygen, which means I have 6 atoms of oxygen. So this is something that you'll find we have to do as we go through equations in an attempt to balance them, which is the next thing that we will try to tackle. Let's take a look at one that might be a bit more complicated. How about we look at Al2 SO4 in parentheses 3 verse 2 Al2 parentheses SO4 parentheses 3. So we want to discuss how the parentheses with a number outside can affect it, because we already know what the 2 does in front. We'll try to do the same thing. I'm going to show you 2 different methods for doing this. The first method is we break it up into each individual element. We have an Al, we have S, and we have O. If we were going to count it here, there's a 1 in front, so we just look at subscripts. There's 2 with Al, which means there's a 2. Now, here's how the parentheses work. The 3 outside distributes only to the things inside the parentheses. So the 3 reaches to O and to S, but it does not make it out to the Al. So if I have 3 times the 1 for sulfur, I have 3 sulfurs. And then for O, I have 3 times the 4 subscript, which means I have 12 O's. Doing the same thing over here, Al, S, and O. Now you have multipliers from both directions. You'll have 3 making it into the O and the S, but now you also have a 2 that makes it to everything. So for Al, now I have 2 times the 2 here, which means we have 4. With the S, I have 2 times the 1, and then there's 3 of them, so times the 3. All right, so 3 times 1 times 2 means we have 6. Same thing here, 2 times the 4 times the 3 means we get 24 of the oxygen atom. Right? So if you have a coefficient in front and there's parentheses, you can get a multiplying effect from that. The other trick I wanted to show you was sometimes, instead of breaking these down, we'll keep them together. They'll say you have Al and then you keep SO4 together. And you'll be allowed to do this if you see more than one SO4. So the idea here is I have 2 Als, and then if I look at SO4 in parentheses, I see there's a 3 outside. I have 3 SO4s in that fashion. Over here, same idea. 2 times the 2 Als would be 4. And now I have 3 SO4s times the 2 in front. I would have 2 times the 3 SO4s. I would have 6. And you will find that we will be doing that as well as we go through the chapter. So this video hopefully helps set up what we're going to learn with balancing equations and then moving on and predicting reactions, but it should be a nice little background that helps you get ready for what the things are to come. If you have any confusion about what we've been doing, particularly the counting atoms, please feel free to come in for some help.